Move to the first speaker of the session. It's Jorge Santos. He's talking about black holes with single killing vector fields and black resonators.
Well, thank you all for inviting me here. It's a true pleasure to be in Bangalore and to give a talk at Strings. I would like to extend a little bit of the complaint that João made. So not only I will leave the luxury of this hotel, I have to return to Cambridge to bad weather, and worse than that, I have to return to my own cooking. So that is not so good. So this work was developed in collaboration with Oscar Diaz and Benson Way, and you can find this on the archive. It's already published. And it's all about black holes with a single killing vector field. But before I actually talk about the subject of my talk, let me start by saying that, for many years I thought black holes were very simple objects. I was not alone. During the 50s and the 60s, that's what people thought, that black holes were very simple objects. We thought they were so simple that we cooked up a bunch of rules for how we thought black holes should behave. So I coined them the 7 pillars of black hole wisdom. We thought that black holes would have 2 killing isometries, because there was something called rigidity theorems. We thought that black holes would have no hair. They should solely be described by their asymptotic charges. We thought the laws of black hole mechanics should hold, in particular, that there should be a constant temperature along the horizon, that the first law should hold, that is to say, variations of the energy should be expressed in terms of variations of the entropy and conserved charges, and then the second law should hold. We believed in all of this. We believed that an infalling observer would cross the horizon without drama. We believed that asymptotic flat black holes are stable. We believed that the cosmic censorship would protect us from naked singularities. God knows why we believed in that. And we believed that if a gravitational system is linearly stable, then it ought to be non-linearly stable. Okay? Out of all of this, only the second law stays. As soon as you move on from asymptotically flat D equals for black holes, nothing of this holds. Okay? So in virtue of the time, I only had time to cover the top number 1 here. Okay? If you want to hear me about the rest, you have to invite me again. So here is the menu of this talk. I'll start with some motivation. Then I'll tell you about 2 seemingly different instabilities that afflict ADS and black holes in ADS. I'll tell you that there are some very, very special solutions called geons, and I'm going to discuss them. And then I'm going to tell you that these 2 very seemingly different instabilities in ADS can actually be connected through a family of black holes, and this is point number 4. And then I'll get to point number 5. Okay? So what is the motivation to study such black holes in ADS? Well, first I'm going to give you a spoiler alert. What we're going to do. We're going to construct novel solution of black holes in ADS4. I'm going to do this in ADS4 because I have trouble solving elliptic PDEs in higher dimensions, but I could do this in higher dimensions as well. And these black holes will evade Hawking rigidity theorem. So this means that you will only have 1 single killing vector field. Incidentally, this theorem has been generalized to ADS, so I have to tell you how they evade the theorem. And I'll get to that. Why are these important? Well, mainly because of the ADS CFT correspondence. At least that's my main motivation. Maybe you're just a general relativist, and then you have another motivation. But this is my main motivation, because this correspondence maps solutions of the Einstein's equations with a negative constant into certain states of the dual field theory. So by studying these black holes, we might be learning something about conformal field theories. And I should stress that the solutions that I'm going to present to you only have gravity. There's nothing else in the game, just gravity. So they lie at the heart of the universal sector, okay, because they just have gravity. And just to make sure we're really on the same footing, this is the only equation I'm going to solve, the Einstein equation, okay? Nothing else. Now, in a different talk, and with a longer time, I would say that even though the instability that I'm going to present here only has gravity, in fact, it basically makes all known SUSY solutions that we know black hole solutions non-linearly unstable. Okay, so my claim is that all known SUSY black holes in ADS5 are actually non-linearly unstable. And if you want to know more about that, ask me after the talk. Okay, let's first tell you about the first instability, superradiance. If you're a relativist, this is your bread and butter. I know here not many people are, so I'm going to try to explain. So imagine that you take a rotating black hole. Okay? A rotating black hole has an ergo region. This ergo region acts like a negative energy reservoir for particles. This means, so here is a picture of an ergo region. There's a black hole here. There's an ergo region, which is this blue surface. This means you can steal energy from a black hole via the Penrose process. How do you do that? Well, we send a particle in, because here you can have negative energy. You split the particle, you send one inside, carries negative energy. By energy conservation, the one that comes out must have a bigger energy than the one that went in. Okay? So this is a Penrose process. By this, you can steal energy from a black hole. But this, intuitively, I'm here using point particles. You can generalize this to the case of a wave. And this is what's called superradiance. And it's known since the 70s that you can steal energy from a black hole in this way, if the frequency is just so. Okay? Now, if you're in flat space, this is all that happens. The wave goes in, steals a little bit of energy, and comes out. But if you're in ADS, or if you consider some Dirichlet walls, you're in trouble, because the wave goes in, steals a little bit of energy, comes out, bounces back in, steals in a little bit of energy, comes out, and eventually the amount of energy that you have in your wave cannot be negligible. Okay? And so you have an instability. And this is what's called the superradiance instability. Now, this picture is remarkably clear, remarkably simple, and yet, to study this, you have to perturb a fairly complicated black hole that was discovered in '68, and this picture was only confirmed last year, okay? This instability. So this is the black hole that we have to perturb. I don't want you to take too many details about this solution, except that it looks a little bit complicated. The other thing that I really don't understand is that we call this the Caridias solution, even though this was invented by Carter. And the other thing I also wanted to note is that this was discovered shortly after the Kerr black hole, very, very shortly, in the same year. Now, this solution depends on two parameters, the mass of the black hole and the rotation, okay, m and a. To study the stability, it is convenient to introduce two other parameters, the angular velocity of the black hole and basically the size of the black hole. But we would like to make the size of the black hole to be some gauge invariant thing, so we're going to take to be the square root of the entropy. And this is what's called often in the GR community the areal radius and the angular velocity. I hope you all know that for a fixed energy, we cannot increase the angular velocity too much, or else we'll get a naked singularity. The bound between naked singularity and the black hole is what's called an extremal black hole, and it has zero temperature or zero surface gravity. So this just means that there is a bound. Okay? The other thing I want you to note is that this solution has two commuting killing fields, d by dt and d by d phi. Because d by d phi is a periodic coordinate, I can expand perturbations about this metric in terms of a wave number m. Okay? And because it's also invariant in the d by dt, I can expand in Fourier modes. What we're going to do is to determine the quasi-normal mode spectrum of this solution. What do I mean by that? I impose some normalizing boundary conditions at infinity. I don't want to spoil my conformal symmetry as asymptotic infinity. And I'm going to impose some regularity boundary conditions as I cross the horizon in ingoing coordinates. This will quantize my frequency. Okay? If you find an imaginary part of the frequency that lies in the upper half plane, well, you plug it back here, and this corresponds to an unstable mode. Okay? So that's what we're going to do. First, let me show you the phase diagram for these solutions. Unfortunately, you cannot see this color very well. So here is the radius of my black hole. Here is the angular velocity. This black line is extremality. Okay, so above here you have naked singularities. Above here you have monsters. Down here you have black holes. Okay? It has long time ago, well, in 2000, been shown by Stephen and Harvey that if you lie in this shaded region, for which all black holes rotate with an angular velocity smaller than 1 in ADS units, the system is very likely to be stable. I'll say very likely because proving that the system is stable is a very complicated statement. They give good arguments for it, but by no means a proof. So what happens up here? Well, up here now we have to discuss, first we need to say which perturbation we're going to put. These perturbations are labeled by my angular number, my angular quantum number, and for m equals to 2, in 2014, we discovered that indeed the superradiance picture is correct, that we have an instability above this line. Okay? So this is the onset of the instability. Any point here should be unstable to m equals to 2. Okay? These points down here will be unstable to other values of m, increasing values of m. Now, even though it's really nice to discuss stability properties in terms of the radius of the black hole and the angular velocity, the story that I like to tell in ADS-CFT goes in terms of the microcanonical ensemble. So I'm going to change variables. I'm going to change now, present the same plot, keep the exact same color coding, but now present the angular momentum versus the energy. Okay? So for fixed angular momentum, my energy cannot be too small, or else I would have an extremal black hole. This is the line of extremality. In this slit here, the black holes are stable. The radius black holes are stable. In this region here, they're unstable to m equals to 2. And now you can ask what happens to m equals to 5. Well, they start filling in this slit here. And you reach omega equals plus equals 1 when m is exactly equals infinity, which is this line here. And this was shown in great generality by Kunduri et al. OK, good. So this is the super-radiance instability. I know you don't like to ask questions in the middle of the talk. I'm still going to incite that. Do you have any questions about the super-radiance instability? No, this is all linearized at the moment. Thank you. OK, so I'm going to change gears. I'm going to talk about a seemingly different instability, which doesn't even have a black hole. OK? Now, I know that you guys don't like this name, the nonlinear instability of ADS, so I'm not going to discuss why this is the name. I'm going to tell you what we mean by this, the nonlinear instability. So this is the problem we want to study. Let's consider a space-time with a certain manifold and a certain metric. And if you have a space-like boundary, you also have to give me some boundary conditions. OK? Now, take a small perturbation in a Cauchy surface of this space-time. Okay? The question that we want to address is, how will this small perturbation evolve with time? And in particular, will my space-time remain smooth in the future, or dragons will appear? That's the idea. Okay? So you take a small perturbation here, you evolve it far in the future, and you see what you get. If you're a mathematician, you actually want to go much further than this. You want to bound the difference from the space-time that you obtained by perturbing it in terms of your initial data. You even want to see how exactly it decays. This is an extremely tough problem to answer in full generality. We're going to focus here on a much more strong, if you want, drastic effect. Imagine that you start with a geodesically complete solution. So imagine just no naked singularities, no black holes. Does the space-time under an infinitesimally, not infinitesimal, under a small perturbation remain geodesically complete? Okay? So if I perturb a space-time ever so slightly, do I necessarily form black holes in the future? Okay? So this is really hard to answer. Let me tell you what's known. Well, at the linear level, it seems that anti-de Sitter space, Minkowski space, and the Sitter space are very similar to each other. There's only one nagging issue. The issue is that in anti-de Sitter space, the waves don't decay. They just stay there back and forth. They don't decay. Whereas in the other ones, they disperse. What about at the nonlinear level? Well, at the nonlinear level, believe it or not, it took a 500-page monogram to show that Minkowski space is stable in d equals 4. If you actually go up in dimension, it's a lot easier to prove. It's one of these things where higher dimensions is your friend. If you're in dimension bigger than 4, it's easy to prove that Minkowski space is stable just because gravity decays much faster. It's also a lot easier to show that Minkowski space is stable in de Sitter because things expand faster. Okay? So what about ADS? This has never been shown for ADS. And I love the way that Gary discusses this. It has never been shown in ADS, well, because it's just not true. Okay, so forget trying to prove this in ADS, it's just not true. The claim is that some small generic but finite perturbations, they can be arbitrarily small, but you have to consider finite size effects, eventually become large and form black holes. Okay? And they don't form black holes in any way, they form black holes in a very specific way. It's very reminiscent of what happens in the case of the onset of turbulence, where you see energy cascading towards smaller and smaller scales. There's also a cascade towards large scales, but I'm not going to discuss this here. Okay, what is the heuristics for this? First time I heard about this result, I just thought, well, these general relativists, they don't know what they're doing. This is very easy to explain. All you're seeing is thermalization. You have a compact system, you put your CFT there, you kick it ever so slightly. What you're expecting the system to do? It will thermalize. Well, this will lead to a formation of the black hole. That's what I thought. Now, this heuristic was great at the time because it allowed us to conjecture something. Maybe if you take very, very special fine-tuned solutions, you can evade this. You just have to be very special. Okay? And indeed, we conjecture that such solutions should exist, solutions that are very special and do not necessarily lead to the thermalization. They're completely non-singular. There's no black holes. They would just correspond to some nonlinear realization of the normal modes of ADS. They would have to be very special, and indeed they are. They're exactly periodic in time. They're completely, horizonless solutions that just go on with time, and they never seem to form a black hole. For those of you that are more GR inclined, they are the analog of nonlinear gravitational plane waves. Now, these heuristics is great, but it's wrong. It's wrong because if you deform the sphere ever so slightly and take an ellipsoid and repeat the same experiment, no black hole will form in the asymptotic future. Okay? So what has been observed for ADS? 2011, Piotr Bizon and Andrei Rostorovsky, they put out a paper that is a tour de force calculation. I encourage you all to read. Here is what they get. On the horizontal axis, I have the amplitude of my perturbation. On the vertical axis, I have the formation or the location of the apparent horizon. If my amplitude is very large, I form a black hole. You know, the wave just goes in and forms a black hole. I keep decreasing the amplitude, and eventually I form a zero-size black hole right at the center of ADS. Now, there's no violation of cosmic censorship because my amplitude is very, very tuned. Now, if I was in flat space, the wave would go through, go off to infinity, and bye-bye, right? But here, the wave will bounce back again. It didn't form a black hole on the first trial, it will form on the second. And this process will repeat ad aeternum. Okay, so sometimes it takes 100 million bounces before it forms a black hole, but eventually it forms a black hole. The time it takes to form a black hole can be predicted using third-order perturbation theory, and it scales like 1 over the energy. So that's the time I would say it takes to thermalize the system. Certain types of initial data do not seem to do this. Okay? Even though they might be generic, they do not seem to do this. We still don't understand this. But because I can only do a certain amount of things at the same time, we decided to focus on trying to understand first why these geons, which are very special, cannot, try to study them. So geons are regular horizon solutions of the Einstein equations, which from the quantum field theory perspective do not seem to thermalize. This is how they look in terms of the stress energy tensor at the boundary. They have pockets of negative energy and positive energy, but the integral over all of this, of course, is positive. They have a single killing field, which also defines their angular velocity, and you should imagine that this figure is rotating with constant angular velocity. This killing field is time-like near the poles, but becomes space-like near the equator. This will be important later. Satisfies the first law, which is great to check numerics, and it's completely unclear if their energy can be made arbitrarily large. We're still fighting to understand this. Okay, so this finishes the second part, which is, trying to understand this other instability. Now I'm going to tell you that one thing that we can do is to put a tiny, tiny, tiny black hole at the center of this geon. Now, if you've been in Santa Barbara for long, the first thing you do when you see a wave is you try to surf it, okay? That's exactly what we're going to do here. We're going to take a geon, which has a very well-defined angular velocity, and we try to surf. Now, in theory, not in practice, but in theory, how do you surf a wave? Well, the wave is going with a certain angular or a certain phase velocity. You align your phase velocity with that of the wave. That's how you do it. In theory, in practice, not quite. Now, this is only possible if the angular velocity of the wave matches that exactly of the geon, okay? But if that's the case, well, then you just found the black hole with a single killing field because the geon only had a killing field. Now, you start scratching your head, and well, in the literature, have I heard about black holes with a single killing field? Well, they were conjectured a long time ago in 2003 by Harvey to exist at the onset of the superradiance. Now you just see, well, maybe all of this is connected because I can have a tiny black hole at the center of a geon that only has a single killing field, and Harvey is promising me that there is also a black hole with a single killing field at the onset of superradiance instability. So this evades the rigidity theorem because the only killing field that you have is precisely normal to the horizon. And this is an assumption that you need the opposite of this in order to prove the rigidity theorem. So we have constructed these solutions. They correspond to 10 coupled 3D nonlinear partial differential equations of the nonlinear type. Bottom line is we know how to solve them. So they are adapted to having just one killing field. This is their line element. You have to solve for these 10 functions. And they're functions of psi, y, and x. Now, they parameterize a two-dimensional phase space. Here, we're going to parameterize the solution by the temperature and some parameter, which we call the wiggliness parameter. Again, for those of you that have been following the advances in general relativity, they have a well-defined temperature, these guys. What have we found? Same plot, okay? Right here, I have the supersymmetric bound in ADS4, okay? Just lies below this line here. Here, I have the extremal black holes, and these points correspond to my new black holes, which we've coined black resonators. They only have one killing field. The first thing that we see is that these black holes do branch from the onset of superradiance, because that's exactly this line here, and then branch from that. The other thing that we see, which is another line that is almost superposed to this one, is that they would continue down to the geons. Now, it doesn't look in this picture, but we have perturbation theory that confirms this picture completely. Okay? So it seems that our black holes just fill in this gap. Okay? From the CFT perspective, this is great. Because from the CFT perspective, we know that the supersymmetric bound is somewhere here. And so it seems that Curry ds was not saturating the supersymmetric bound. Okay? But it seems that these black holes are saturating or are going towards the supersymmetric bound. So they fill in the gap that was missing from the CFT perspective. And this is exactly the same statement. These black resonators seem to exist even past the extremality of the Curry ds black hole. Whenever they coexist, they have a higher entropy. And it's a second-order phase transition. Furthermore, the horizon of these black holes is deformed along the direction that they rotate. So now you might think, well, they're radiating if they're deformed along the direction that they rotate. And they are. The point is, because you're in ADS, the radiation is coming just about at the same rate so that it can be in equilibrium with its own classical radiation. Now, are these possibly the end point of the instability that I alluded to? So following on your question, let's try to see if we can now extend this to the full nonlinear level. Well, if this was restricted just to one mode, if gravity was kind enough so that this dynamics would be restricted to one mode, possibly yes. It's very similar to holographic superconductors, so possibly yes. The problem is that the m equals to 2 mode is stable in a region where the m equals to 3 mode is still unstable. So you put there a generic perturbation, the m equals to 2 mode will grow. After the m equals to 2 mode grows, it looks at the m equals to 3 and says, oh, oops, I'm still unstable to m equals to 3. And it will keep going, and will never stop. Which evidence do we have for this? Well, the first thing we have as evidence is that the central black hole is still very similar to a Curry ds black hole. And the Curry ds black hole is still unstable in that regime. Finally, for higher m, one can check that there are very, very similar black resonators for other values of m, and that they have increasing entropy with m. So even though we found the metastable state, because it has higher entropy than the Curry ds black hole, there is another state with a higher value of m, and the higher m you have, the more entropy you have. So the system will keep cascading towards higher m. So if I only had this would just be words, but now I have a theorem. Well, I didn't prove the theorem, but somebody was kind enough to prove that the solutions that we just found here are all unstable. Even though they have a higher entropy than that of Kerr, they're all unstable, which means that the system cannot possibly stabilize in one of these solutions. It will just keep evolving with time. Okay? And this is by now a theorem. So this puts some meat in a conjecture that we did in 2011, that there is no classical endpoint for the superradiance instability. Basically, you will have modes that keep going, flowing to smaller and smaller frequencies, and eventually you'll need quantum effects to sort out what's happening. So it's a moral violation of the cosmic censorship. Conclusions. We have constructed black holes with a single killing field. They interpolate between the onset of superradiance and the geons, and they correspond to a new phase that dominates a microcanonical ensemble, in the sense that there is a second-order phase transition. Now, what can you ask me after the talk? Does this mean that there is infinite non-uniqueness for Curry ds? How large is it? What is the story in the canonical and grand canonical ensembles? Is it very similar? So these questions, I know how to answer. Questions that I do not know how to answer. What is the field theory interpretation of this phenomena? I would love to know the answer. Can we make a connection with glassy physics? It seems so, because we have some scales that are flowing towards and some energy that's flowing towards and towards smaller scales, but the system is never quite thermalizing, because it keeps evolving in time. It smells a little bit like a glass. Well, and there's many more. Thank you.
Other questions, comments?
Hey, Shiraz.
If I understand right, you have one of these hairy black holes parameterized by m. You have a black hole solution for every value of m.
That's right.
Now, if you take m to infinity, presumably the solution becomes non-analytic. But does the entropy of the black hole, does the thermodynamics of the black hole have a good m goes to infinity limit?
Yes.
So could that crazy non-analytic looking state represent in some moral sense the endpoint of your superradiance?
Well, thank you for your question. So what Shiraz is asking is the following. In the solution that I showed, I told you that m equals infinity would stabilize at omega equal to 1, and maybe it's a possible endpoint for this. Okay? So I cannot rule that out, but I can try to search for that solution, and I didn't find it.
But it's going to be very, it's not going to be an analytic solution.
No, right. So there's 2 points with that. First, I don't know if the curvature of that thing is small, okay? And if it's very, very, very large, you're in trouble. And I don't know if it will be, continue to be very, very large with time.
But the thermodynamics is smooth.
Well, I can only say that in perturbation theory, but I can say that the entropy of these guys are very similar to the entropy of a Kerr black hole with ADS, but I cannot tell you much more than that.
Thank you.
Any other questions? Yes?
So, what is the scaling of the entropy with M in this case?
It's something like, it goes as 1 over m, basically. So it's a number plus 1 over m.
And do I understand correctly that in the other ensembles, the solutions with omega greater than 1 never dominate, so therefore they're a priori sort of subdominant saddles in the ensembles to start with?
Well, right, so this is a story that I think is very interesting in the macrocanonical ensemble. In the other ensembles, I think it's a little bit less interesting because ADS will always be thermally stable. However, I was expecting some of you to say, why do you think supersymmetric black holes are unstable? Okay? And because none of you will ask, I will answer anyway. So all supersymmetric black holes in ADS5 turn out that they need the angular velocity to be exactly 1. Supersymmetry demands that. Okay? But to have an angular velocity that is exactly 1, it's very, very easy to construct open sets of perturbations, and indeed we've done it, that take it to an angular velocity that is bigger than 1. But if the angular velocity is bigger than 1, your system will be unstable. Okay? So although I agree with you that from the perspective of the grand canonical ensemble or the canonical ensemble, they're a little bit less interesting, these questions for supersymmetric black holes seems very pertinent. Because they have exactly omega exactly equal to 1.
One more question?
Sorry?
Can you repeat the question?
I thought that ADS does not have a well-defined Cauchy problem. So what are the boundary conditions?
No. Yeah, it has a well-defined boundary Cauchy problem. This was proved by Friedrich, I think. No, yeah, Helmut Friedrich. Energy-preserving boundary conditions? Only 1.
Okay, let's thank the speaker.